Welcome to the National Institutes of Health, Office of Intramural Training and Education's webinar on Laboratory Math 2, Solutions and Dilutions. This webinar is intended to give a brief introduction into the mathematics of making solutions commonly used in a research setting. While you may already make solutions in the lab by following recipes, we hope this webinar will help you understand the concepts involved so that you can calculate how to make any solution. A textbook definition of a solution is a homogeneous mixture of two or more substances. These mixtures can be in any form of matter. However, for this webinar we are going to focus exclusively on liquid solutions. In a laboratory setting, solutions are an essential part of research. There is a reason that bench research is often referred to as wet research. Most biochemical reactions occur in liquid solutions. This should help explain why dehydration is such a life-threatening ailment. Without water, the body is unable to perform many of the biochemical functions necessary to survive. In the laboratory, solutions are everywhere. Buffers, reaction mixtures, cell culture media, cell lysates, liquid acids and bases are all examples of solutions commonly used in the lab. We talk about solutions in terms of concentrations, how much of each substance or solute the solution contains. Concentrations can be recorded and reported in many different ways depending on the solution, the scientist, and what the solution is being used for. Let's review a few of the common ways of reporting concentration. Molarity is used to report molecules of a substance per unit volume. Specifically, molarity is the number of moles of a substance per liter of the solution. It is reported in moles per liter, or with a capital M for molar. Mass per unit volume is often used to report the concentration of proteins and other complex substances with molarities that are not easily determined. So the concentration of a complex solution of proteins often is reported as grams per liter. Normality is like molarity, but is used for ionic solutions to more accurately represent their ionic strength. A single molecule of an ionic compound may, when in solution, separate into individual charged particles. For example, NaCl in solution consists of positively charged sodium ions and negatively charged chloride ions. What is relevant is solute particles per unit volume, or ions per volume. So, normality is the number of moles of active ions per liter in a solution. Acid and base concentrations are often expressed in normality. Before you can make a solution, you need to know a few things. In this case, we will be looking at how to make a solution from a solid substance, or solute, being dissolved in a liquid, or solvent. To do this, you need to know the desired concentration of the completed solution. That means, how much of your substance per unit volume do you want when you are finished making your solution? You will also need to know what units you will be reporting the concentration in. If you are reporting in molarity or normality, you will need to know the molecular or formula weight of the substance. That is to say, you need to know how many grams of the substance are in a mole. You need this information because we cannot readily measure the number of moles of a substance, but we can measure the mass. So we use the mass and the molecular weight to determine moles. The molecular weight is determined by the elemental composition of the compound and is usually listed on the container the solid solute is stored in. You will also need to know the desired volume of the finished solution. Let's take a look at a simple example. How would we make 1 liter of a 5 molar solution of a substance with a molecular weight of 75 grams per mole? The first thing to determine is, what don't we know? We know the volume, the molarity we want, and the molecular weight. What we need to know is how many grams of the substance we need to measure out. So our approach is to first determine how many moles we need of the substance, and then use the molecular weight to determine how many grams we need to weigh out. It is important to note that the concentration multiplied by the volume, or CV, is equal to the total amount of substance. A 5 molar solution means we have 5 moles per liter. And we want a total of 1 liter. If we multiply 5 moles per liter times the total volume of 1 liter, we get our total number of moles needed for our solution, which is 5. To determine the number of grams we need, we multiply the number of moles by the molecular weight, which is grams per mole. We know that the molecular weight of the substance is 75 grams per mole, and we need 5 moles. So we can multiply the 5 moles needed by the 75 grams per mole, and we can solve that we need 375 grams of the substance. So we can weigh out the 375 grams of the substance, and then bring the volume to 1 liter with solvent. It is important to note that you do not add 1 liter of solvent to the 375 grams of the substance. The dry substance has a volume as well, and if you add a liter of solvent, your total volume will be greater than 1 liter, and your concentration will be wrong. Solutions in a research setting often have more than just one solute component. Complex solutions are those that contain 2 or more chemical compounds in addition to the solvent. To make a complex solution with solid solutes, you treat each solute individually when determining the mass of that compound to add to the solution. For example, to make a 5-liter solution of 50 millimolar NaCl and 10 millimolar tris HCl, you would first determine the mass of the NaCl you need. Then, you would determine the mass of the tris HCl you need. You would weigh out both individually, add them to the desired container capable of holding 5 liters of liquid, and then you would bring the volume to 5 liters of volume with water while mixing. Let's go ahead and work out the arithmetic for this solution. First, we need to determine the mass of the NaCl that we will need. We know we need the final concentration to be 50 millimolar, which means we will need 50 millimole of NaCl per liter of solution. Remember that CV equals total amount, so we multiply 5 liters by 50 millimoles per liter. The liters cancel out, and we know that we need 250 millimoles of NaCl. We also know that we can convert 250 millimoles into moles by dividing by 10 to the negative 3. This lets us know that we need 2.5 times 10 to the negative 1 moles of NaCl. We can then multiply this by the molecular weight of NaCl, which is 58.44 grams per mole. The moles cancel out, and we get 146.1 times 10 to the negative 1 grams, or 14.61 grams of NaCl. Note that the significant digits will be determined by the scale you will use to weigh out the compounds. Next, you will need to determine how much tris HCl you will need. The molecular weight of tris HCl is 157.56 grams per mole. Can you work out how many grams we will need for 5 liters of a 10 millimolar solution? Again, determine how much mass you need to weigh out by multiplying concentration by volume. In this case, 5 liters times 10 millimoles per liter. This will give you 50 millimoles, or 5 times 10 to the negative 2 moles. Then, multiply this by the molecular weight of 157.56 grams per mole, and you get 7.88 grams. Add that to the container and bring the volume to 5 liters with water. One of the benefits of working with liquid solutions is the ability to dilute them. Dilution is a technique that uses a solvent to increase the volume of a solution and thus decrease the concentration of that solution. It is a concept used in everyday life as well. If your coffee is too strong, you add water to dilute it and make it more palatable. Many people do this with their juice or other beverages. It can also happen inadvertently when your ice melts and makes your favorite carbonated soft drink taste less sugary. In science, diluting solutions has practical applications as well. Oftentimes, you'll need a small volume of a low concentration solution. When you do the math, you find that you need to weigh out microgram or nanogram amounts of the compound. For example, how much glucose would you need to make a 50 milliliters of a 1 micromolar solution? The molecular weight of glucose is 180 grams per mole. Take a minute to work it out. Did you come up with 9 micrograms? Lab balances are not up to the task. So, you make a higher concentration solution and then dilute it to the concentration you need. The more concentrated solution is often called a stock solution. You can dilute the stock solution to the concentration you need, which is often referred to as a working concentration or final concentration. Example of stock solutions are a 5 molar solution of NaCl or a 2 molar solution of tris HCl. It is important to understand that when you are diluting a solution, you are not removing any of the solute. The total amount or mass of the solute does not change. If you have 50 milligrams of compound X in 100 milliliters and you dilute the whole thing to 1 liter, you now have a concentration that is 1/10 what it was before. You still have 50 milligrams of compound X. It is just in a larger volume. As you have worked out in a few previous examples, the concentration multiplied by the volume equals the total amount of the compound. Since the total amount doesn't change, it means that the initial concentration multiplied by the initial volume will equal the final concentration multiplied by the final volume. This gives rise to the equation C1V1 equals C2V2. You might also see this written CIVI equals CFVF, where I indicates initial and F stands for final. When making dilutions, you will know 3 of the 4 variables from the equation C1V1 equals C2V2. You will know your initial concentration, or the concentration of the stock solution you are about to dilute. You will know the final concentration of the solution that you will want to be working with, and you will know how much of the final solution you will want to be making up. What you will need to solve for is how much of your initial stock solution will you need to add to the final solution to get the desired concentration. To do this, you can just divide both sides of the equation by your initial concentration, C1. This yields the result that V1 equals C2 times V2 divided by C1. Let's work through an example of this together. I mentioned in a previous slide that a common stock solution in a lab is 5 molar NaCl. This would be our initial concentration. If we want 100 milliliters of 0.5 molar NaCl, 100 milliliters is our final volume, and 0.5 molar is our final concentration. We can plug these values into the equation C1V1 equals C2V2 and solve for V1 by dividing both sides by 5 molar. The molars will cancel out, and we will get 50 millimolars divided by 5, which means our initial volume is 10 milliliters. This means that you add 10 milliliters of the 5 molar NaCl stock solution to a container and then bring the volume to 100 milliliters with water. Just like with solid solutes, we can make complex solutions from multiple liquid stock solutions for different compounds. To do this, we treat each dilution individually to determine the volume we need of each stock solution. Then we combine them all and bring the result to the appropriate final volume. Let's look at an example. What we want is a working solution of 250 milliliters that is 0.1 molar NaCl and 0.5 molar tris HCl. What we have is 5 molar NaCl solution and 1 molar tris HCl solution. We know that V1 is equal to C2 multiplied by V2 and divided by C1. So we start with NaCl and plug in our values and see that V1 is equal to 0.1 molar times 250 milliliters divided by 5 molar. The molars cancel out and we solve that we need 5 milliliters of our 5 molar stock NaCl solution. Okay, now you work out how much tris HCl we need. Again, we plug in the values of the tris HCl that we know. 0.5 molar for C2, 250 milliliter for V2, and 1 molar for C1. The molars cancel out and we solve that we need 125 mL of 1 molar tris HCl. So we add 5 milliliters of NaCl and 125 milliliters of tris HCl and then bring the volume up to 250 milliliters with water. Note, if we needed a much larger concentration of tris or had to add aliquots of several other solutions, this might not work. We would need more concentrated stocks or to add some solutes as solids. It should come as no surprise that you can even make complex solutions from a combination of solid solutes and dilutions of liquid stock solutions. To do it, you again will treat each compound or stock solution individually. It is best to do things in a particular order. Determine the mass of the solid compound or compounds that you will be dissolving. Then, determine the volume of the stock solution or solutions you will be diluting. Add the solids to the container, then the stock solutions, and finally, bring the whole solution up to your desired final concentration. On the next couple of slides, we'll be going through some practice problems and making complex solutions from a combination of solids and liquids. So let's start by working with some familiar compounds. What we want for a final solution is 10 millimolar tris HCl, 25 millimolar NaCl, and a total volume of 250 milliliters. You're starting with a 2 molar stock solution of tris HCl and solid NaCl with a molecular weight of 58.44 grams per mole. So, how much of what are you going to use to make this solution? Start by finding the mass of NaCl you will weigh out and add. We know we want 25 times 10 to the negative 3 moles per liter and a total volume of 250 times 10 to the negative 3 liters. We multiply these together to get the total number of moles of NaCl we will need in the solution. In this case, 6.25 times 10 to the negative 3 moles. We then multiply that number by the molecular weight of 58.44 grams per mole to get the total mass of NaCl we'll need. This equals 0.36 grams of NaCl, which can be measured on most laboratory scales. Next, we use the equation C1V1 equals C2V2 rearranged to read V1 equals C2V2 divided by C1. We plug in our known numbers of 10 times 10 to the negative third moles per liter final concentration, 250 times 10 to the negative 3 liters for final volume, and divide that by 2 moles per liter initial concentration. The moles per liter will cancel out, and we will get 2.5 times 10 to the negative 3 liters divided by 2, or 1.25 milliliters initial volume of our 2 molar tris HCl solution. So, we add the 0.36 grams of NaCl to the container. Then we add the 1.25 milliliters of 2 molar tris HCl to the container. And finally, we bring the volume to 250 milliliters with water. So, how did you do? You can replay this slide or any previous slide if you need to review any of the concepts. How about one more example? Okay, same compounds, but we are going to change the concentrations of each and the total volume. Now, what we want for a final solution is 1 millimolar tris HCl, 25 micromolar NaCl, and a total volume of 1 milliliter. What you have to start with is a 1 molar stock solution of tris HCl and solid NaCl with a molecular weight of 58.44 grams per mole. So, work the numbers to find out how much of each compound you will need to make the solution that you want. Again, we start by finding the mass of the NaCl you will weigh out and add. This time, we have 25 times 10 to the negative 6 moles per liter and a total volume of 1 times 10 to the negative 3 liters. We multiply these together to get the total number of moles of NaCl that we need in the solution. In this case, 25 times 10 to the negative 9 moles. We then multiply that number by the molecular weight of 58.44 grams per mole to get the total mass of the NaCl that we will need. This equals 1,461 times 10 to the negative 9 grams, or 1.46 micrograms of NaCl. This is a very small amount to measure, but let's move on to our volume of tris HCl. Again, we use the equation C1V1 equals C2V2 rearranged to read V1 equals C2V2 divided by C1. We plug in our known numbers, 1 times 10 to the negative 3 moles per liter final concentration, 1 times 10 to the negative 3 liters for final volume, and divide that by 1 mole per liter initial concentration. The moles per liter will cancel out, and we will get 1 times 10 to the negative 6 liters divided by 1, or 1 microliter initial volume, or of our 2 molar tris HCl solution. Now we face a problem. There are few scales that can measure that small of a mass of a compound, and while some micropipettes can accurately transfer 1 microliter, it is such a small volume that there is a high rate of error. So, what do? We perform serial dilutions. The previous slide demonstrates a common problem faced in a biomedical research lab. While using very little of a compound is always a financial benefit, it can be a practical hurdle. When you need a volume or an amount that is too small to accurately measure, you have a couple of options. You can make a much larger volume of the solution that you need at the proper concentration. For example, we needed 1.5 micrograms of NaCl for a 1 ml solution. We could make 10 liters of the solution and weigh out 0.015 grams of NaCl. But then, we'll have almost the entire 10 liters of our solution left over, and a 10-liter carboy is quite the space eater in the lab. The other option is to make a small volume of a much higher concentration solution. Then, you can dilute that solution down to the concentration that you need. Oftentimes, you will need to dilute the higher concentration solution a significant amount, which would again require making a larger volume of the solution at the concentration you need. However, we can use a series of small dilutions into smaller volumes to get to the volume and the concentration that we desire. This is known as using serial dilutions. While serial dilutions are a great way to save on both reagents and space in the lab, they have other experimental uses as well. We won't be covering those uses in this webinar, but it is likely you will come across their uses if you work in the lab long enough. When preparing to perform serial dilutions, there are three main components to consider. Like many things in life, it is important to know where you are starting and where you hope to end up. In this case, you will need to know the initial concentration you will start your dilutions with, and you will need to know the final volume and concentrations you will want. You will also want to determine your dilution factor. The dilution factor is the factor by which you will dilute your sample at each step. Mathematically, it is equal to the sum of the volume of your stock solution you are adding and the volume of the solvent you are making the dilution in, divided by the volume of your stock solution. So, if you are adding 100 microliters of your concentrated solution to 900 microliters of your solvent, your dilution factor would be the sum of 100 microliters plus 900 microliters divided by 100 microliters. This would mean your dilution factor is 10. Finally, you will need to know the number of dilutions you are going to use to get from your initial concentration to the final concentration at the volume that you want. Again, this can be determined mathematically. The number of dilutions is equal to the number of times the dilution factor will be multiplied by itself to equal the starting concentration divided by the final concentration. So, with a dilution factor of 10, 10 to the x is equal to the starting concentration divided by the final concentration. In this case, we will use 1 molar as our starting concentration and 1 micromolar as the final concentration. So, 10 to the x power would be equal to 10 to the 6 power, and we will need to do 6 dilutions in this case to get to our final concentration. Please note that this example assumes that all dilution steps are the same. They need not be. It is also important to note that x may not be a whole number. In this case, you will either want to change your dilution factor or use a combination of dilution factors. We will consider an example of that in a couple of slides. Let's take a look at this particular serial dilution in cartoon form. We start with a stock solution with a high concentration. We determine we would perform dilutions of 100 microliters of the stock solution into 900 microliters of a solvent. This first dilution yields a concentration that is 1/10 the stock concentration. After assuring proper mixing, we will take 100 microliters from the first dilution and place it into 900 microliters of solvent in a new tube. This will again be 1/10 dilution, giving a concentration that is 1/100th of the stock solution. This step is repeated 4 times, assuring proper mixing at each dilution. Our final concentration then is equal to the stock concentration divided by our dilution factor of 10 to the 6th power. For our first example, let's take a modified version of a previous example. We want 1 milliliter of 2.5 micromolar NaCl. To make this, we are going to start with 1 milliliter of 2.5 molar NaCl. For practice, how much NaCl will you need? I hope you came up with 0.146 grams. We will use 10 microliters of each concentrated solution. If we will have a final volume of 1 milliliter, how much diluent, in this case water, will we need in each tube? And knowing that, what is the dilution factor? The volume of water is 990 microliters. Add this to the 10 microliters we will be adding, and divide that sum by 10 microliters, and we get a dilution factor of 100. So, how many dilutions will we perform? Again, the number of dilutions is equal to the number of times the dilution factor is multiplied by itself such that it is equal to the initial concentration divided by the final concentration. So, 100 to the x will equal 10 to the 6. 100 is equal to 10 to the 2. Therefore, 10 to the x is equal to 10 to the 2 times x. And if 10 to the 2x equals 10 to the 6, then x equals 3. In this case, we will make 3 sequential or serial dilutions. Okay, now it is time to set it all up and work through the serial dilution step by step. We have already done the first step, which is to plan it out. The next step is to set it up. First, make up your solution with your starting concentration. In this example, we need to make up 1 milliliter of 2.5 molar NaCl. Last slide, we determined that we need 0.146 grams NaCl. So weigh it out and place it in a tube and bring the volume to 1 milliliter with water. Now, set up your tubes for the serial dilution. We know we will need 3 dilutions. This means we will need 3 tubes, each one with 990 microliters of water. Add 10 microliters of the 2.5 molar NaCl to tube 1 and mix well. Now, how much volume is in tube 1? 1 milliliter. And what is the concentration of tube 1? If the dilution factor is 100, we should now have a 25 millimolar NaCl solution. Now, add 10 microliters from tube 1 to tube 2 and mix well. You will again have 1 milliliter total volume in tube 2, but what concentration do you have? 250 micromolar. Again, add 10 microliters from tube 2 to tube 3 and mix well. And the final concentration and the volume of tube 3 is 1 milliliter of 2.5 micromolar NaCl. I mentioned earlier that sometimes x, the number of dilutions required, will not be a whole number. To look at a situation like that, we will make a small modification to the last example. This time, we want 1 milliliter of 25 micromolar NaCl. Again, starting with 1 milliliter of 2.5 molar NaCl. We will again use a dilution factor of 100. So, how many dilutions will we perform? Again, if the number of dilutions is equal to the number of times the dilution factor is multiplied by itself to equal the initial concentration divided by the final concentration, then 100 to the x is equal to 10 to the 5th. In this case, we will need to make 2.5 dilutions. So what happens now? The easiest thing to do is to start with the integer to the left of the decimal point, which in this case is 2, and make 2 dilutions with the dilution factor of 100. If you plug that back in, you get 100 squared, which is 10,000, or 10 to the 4th. If you divide the 10 to the 5 you needed to dilute your sample in total by 10 to the 4, you will do with your first dilutions. That leaves you with a factor of 10. So, you can dilute your second dilution by 10 to get the final concentration that you need. So, you can perform 2 dilutions with a dilution factor of 100, and then do the third dilution with a factor of 10. Let's take a look at this in practice. Again, let's set this serial dilution up step by step. First, make up your solution with your starting concentration. Weigh out 0.146 grams of NaCl and place it in a tube and bring the volume to 1 milliliter with water. Now, set up your tubes for a serial dilution. We know we will need 3 dilutions. 2 dilutions with 10 microliters going into 990 microliters, and 1 dilution with 100 microliters going into 900 microliters. This is your dilution factor of 10. This means we will need 3 tubes, 2 with 990 microliters of water, and 1 with 900 microliters of water. Just like before, add 10 microliters of the 2.5 molar NaCl to tube 1 and mix well. The concentration is now 25 millimolar. Then, add 10 microliters from tube 1 to tube 2 and mix well. What concentration do you have now? 250 micromolar. This is an important step to double check and make sure your plan will work. Will diluting 250 micromolar by 10 give you the desired concentration of 25 micromolar? Yes, it will. Now you can add 100 microliters from tube 2 to tube 3 and mix well, and the final concentration and the volume of tube 3 is 1 milliliter of 25 micromolar NaCl. So let's look at something a little different. Oftentimes, you start with concentrations of your stock solution that are not factors of 10 away from your desired final concentration. Take, for example, having a 3.45 millimolar stock solution of NaCl and wanting 200 microliters of 100 nanomolar NaCl. What would you do first? I would recommend making a dilution that makes the serial dilutions more simple by creating a concentration that is factors of 10 away from your desired final concentration. In this case, I would make a 1 to 3.45 dilution to give us a 1 millimolar solution. Note, I recommend that you do not use 1 microliter of your stock solution and pipetting into 2.45 microliters of solvent. That small of a volume can lead to pipetting errors. Use 10 microliters of your stock solution and 24.5 microliters of solvent. Then, determine your dilution factor. You can either do this by setting the dilutions you want to do, or by looking at the equation dilution factor to the power of x is equal to the initial concentration divided by the final concentration, and then deciding on a strategy from there. To do this, simply divide the initial concentration by the final concentration, in this case 1 millimolar, our new starting point, divided by 100 nanomolar to get 10 to the power of 4, or 100 squared. A dilution factor of 100 would mean 2 dilutions. Now, go back to the equation for determining the dilution factor and realize that Vs plus Vdil needs to equal 200. You can then solve for Vs1 by plugging in the numbers and solve that Vs1 is equal to 2, and thus Vdil equals 198. Now we just have to set it up from step 1. Our first step is to make our 1 to 3.45 dilution. To do this, we add 10 microliters of our stock solution to 24.5 microliters of solvent. This gives us a new concentration of 1 millimolar. After proper mixing, we would then add 2 microliters of this dilution to 198 microliters of solvent to give us a concentration of 10 micromolar. Again, after proper mixing, we would transfer 2 microliters into 198 microliters of solvent, and we would have 200 microliters of 100 nanomolar NaCl. Thank you for working through the laboratory math webinars. Please visit our website and check back often for updates to other training materials and programs offered through OITE.